Chapter 1, Fundamentals of Thermodynamics. Section 1.6, Pure Gases, Liquids, and Solids. In the previous video, we calculated the finite size of one xenon atom and one water molecule. And because of the finite sizes of those atoms and molecules, we need to modify the ideal gas equation, PV equals nRT. We need to replace this V to V minus MB. This MB takes account the finite size taken up by the atoms or molecules. V is the volume of the container. MB will give us the space being taken up by those gas particles. B is the size of one individual atom or molecule multiplied by Avogadro constant. So B is approximately the molar volume of the solidified gas. For example, if we solidify water vapor, it's just ice, and we know the molar volume of ice is roughly 20 milliliters per mole. Therefore, this parameter B for water is roughly 20 milliliter per mole, or 0.02 liters per mole. The modified equation will become this: P is nRT over V minus MB. And we divide the numerator and denominator by N, we get RT over molar volume minus B. And this equation shows that when B is larger, the pressure is larger. When B is smaller, the pressure is smaller. When the molar volume and B are close to each other, P becomes infinity. And that indicates the repulsive force when we try to squeeze two gas particles together. Now here's an example problem 1.6.4. Rank the parameter B for helium, neon, argon, and xenon. Well, B is the measure of the size of the gas particles, and therefore the value of B of helium is the smallest. The value of B of xenon is the largest. Now we rank methane, ethane, and propane. We can tell propane is larger than ethane, ethane is larger than methane. Again, B is a measure of the size of the gas particles. B also is a measure of the repulsive force when we try to squeeze two such gas particles together. Now, let's review this. When we take the finite size of an atom or molecule into account, we need to modify the PV equals nRT equation to this. P is now nRT over V minus MB. This equation often overestimates the pressure of the real gases, because between real gas particles there is not only repulsion but also attraction. If we introduce attraction into this equation of gas, it becomes P is equal to RT over molar volume minus B, and then minus, over here we have a attraction term A divided by molar volume squared. Also, we can rewrite this equation to be nRT over V minus MB, and then we subtract AN squared over V squared. The values of A and B are always positive. Again, B is the measure of the size of the molecule, and also B is the measure of the repulsion. And A, on the other hand, is a measure of the attraction between the gas particles. When A is larger, P is smaller. When A is smaller, P is larger. This is because the attraction between gas particles reduces the momentum change of the gas particles during collisions. Now let's rank the van der Waals parameters A for these four different atoms: helium, neon, argon, and xenon. Although they are all noble gases, xenon has the largest A due to the so-called dispersion force. It's just because xenon is larger than argon, argon is larger than neon and helium, and since we have a larger radius in xenon, that means the valence electrons in xenon is farther away from the nucleus. It's easier to distort the shape of those valence electrons to create a so-called instantaneous dipole moment in xenon. And this instantaneous dipole moment can induce another dipole moment in another xenon atom nearby, and these two dipole moments may have attraction. Therefore, xenon has a larger A than the other three noble gases. For the same reason, propane has a larger A than ethane than methane. Now let's look at one numerical example, 1.6.6. We will use the Van der Waals equation to determine which gas has a higher pressure, helium or argon. Remember, argon has a larger B than helium, and also argon has a larger A than helium. Well, this simply means the size of an argon atom is larger than the size of a helium atom, and also the attraction between two argon atoms is larger than the attraction between two helium atoms. These two gases, let's assume, have the same molar volume, 25 liters per mole. Let's assume the temperature is 25 degrees Celsius. We can easily calculate the ideal gas pressure, so I usually just use Wolfram alpha, and I actually type up the equation PV equals RT to get this ideal gas pressure. Now we're going to use this Van der Waals equation. Again, we need to plug in the values of the Van der Waals parameters A and B. So now, this is the Van der Waals equation. Pressure is RT over the molar volume minus B minus A over molar volume squared. And then we plug in the values of A and B. For helium, the value of A is 0.03 bar liter squared over mole squared. The value of B is 0.0238 liter per mole. Again, this number, this parameter B, is actually the size of one helium atom multiplied by the Avogadro constant. We set up the same equation but different values of A and B. If you compare this B and this B, you can see argon has a larger B than helium, and also argon has a larger attraction than helium. So after plugging numbers, we got two different pressures: 0.9925 for helium, 0.9907 for argon. So for helium, its Van der Waals pressure is greater than the ideal gas pressure. For argon, it's a little smaller. This is a little smaller than the ideal gas pressure, mainly because of the large attraction between argon atoms. Example problem 1.6.7. Use the Van der Waals equation to determine which gas has a higher pressure, helium or argon. This time we have a different molar volume than example problem 1.6.6. So we have a larger molar volume here, and the ideal gas pressure, again, it's 0.09916. It's very close to this value, except that this is just 10 times smaller, because this molar volume is 10 times larger. Now let's think about this. If we have a larger molar volume, those gas particles are farther away from each other than the previous example. That means we have smaller attraction and a small repulsion. So we predict the Van der Waals pressures of helium and argon in this example should be really close to the ideal gas pressure. But again, let's just plug in the numbers. Pay attention to the units. For helium, we get 0.09917, just slightly above this ideal gas pressure. And for this argon gas, it's 0.09915 bar, slightly smaller than ideal gas. Again, all three numbers are very close to each other. It's just because although helium and argon are real gases, due to this very large molar volume, those gas particles are really far away from each other, and they have much smaller repulsion and much smaller attraction in this example problem than in the previous one. That's why the van der Waals pressure is really close to the ideal gas pressure. Also, we can look at the formula. So when this Vm is really large, B compared to molar volume can be neglected. And also, when this molar volume is really large, this A over molar volume squared can be neglected. That's why, when we have a large molar volume, the gases behave more ideally. Now another numerical example, problem 1.6.8. This time we'll look at HCl. And we put 2 moles of HCl in 50-liter container at room temperature. And now we're going to use the ideal gas law, PV equals nRT, and the more realistic van der Waals equation to calculate the pressure. We have the parameters A and B for HCl. You can get those values from the appendices, chapter 00, table of content and appendices. We have the molar volume here. We can easily calculate the ideal gas pressure, 0.9916 bars, using this formula. We can also calculate the van der Waals gas pressure by introducing parameters A and B in the equation. Again, it's RT over Vm minus B. So again, B take the finite size of the molecules into account, and A takes the attraction between HCl molecules into account. After we plug in the numbers, we get 0.9873 bars. So if we compare these two numbers, I think this van der Waals gas pressure is a little smaller than the ideal gas pressure, mostly due to the attraction between the HCl molecules. And now we can see the percent error of the ideal gas calculation is 0.44%. It depends on your goal. I mean, sometimes we say this is really small. We view this HCl as an ideal gas. But if you need a higher level of accuracy, we can look up the values of those van der Waals parameters A and B and calculate the van der Waals pressure of HCl, and this number 0.9873 is closer to the actual pressure of this real gas. Another numerical problem, still HCl, but this time we have 2 moles of HCl inside a smaller container. This time it's only 5 liters. And we still do the numerical calculation. Over here, if you click this, you'll get to this Wolfram Alpha page. You get ideal gas pressure 9.916 bars. It's just 10 times larger than the previous calculation when we have 50 liters. Okay, 50 liters, and now this one is 5 liters. And we also calculate the van der Waals gas pressure. Over here we get 9.486. This is the setup of the calculation, but I used Wolfram Alpha to do the calculation. You can see the real gas pressure is lower. That's because the attraction term overweighs the repulsion term. And when this molar volume is smaller, HCl molecules get closer to each other. That means we have larger attraction and also larger repulsion. And in this case, still, the attractive force is predominant. That's why the real gas pressure is smaller. Actually, in this case, it's significantly smaller. 9.5 is significantly smaller than 9.9. In rare cases, the attractive force and repulsive force may cancel each other, and then in that case, the van der Waals equation and the ideal gas equation result in the same number by coincidence.